Assalamualaikum and very good afternoon. Do you have any question regarding the exercise last week? Izas Wilfred. Ada soalan tak? The exercise last week. The assignment should be actually sent by today, but I will extend it by tomorrow. Kong, have you finished?
Sorry, Doctor. Yeah, I haven't done the number C. Question 2C.
Why?
Because I'm not sure about my answer.
Anyone else got problem? You can discuss.
Tempat submission memang belum lagi.
Belum ada.
Untuk assignment 1.
So siapa ada problem boleh share lah. Before we proceed to the new one. Do you have any question? The rest? No question at all. Just now, what is your? You said you're not sure about the question C. What is it, Kong?
So far, I still can deal with it. No any problem.
Okay. So you just don't have not finished that.
Doktor, saya nak tanya. Yang soalan situ dia cakap pasal sketch. Memang sketch lah sebelum makan macam tu je.
Sketch lah, sketch.
Tak perlu exact value macam tak payah.
Ya, tak perlu.
Tulis berapa banyak D punya height tak payah.
Yes, just sketch how you place the reinforcement.
Alright, thank you.
Okay, if there's no question about last week, so I presume that all of you have understand what is the principle of the design, how to analyze the section, especially for the rectangular section. If you don't fully understand, you cannot understand just half. You need to fully understand that. So if you don't understand, do not fully understand, so I'm afraid you cannot understand for this flange section. Okay. Okay, we also have
Doktor.
Okay. Apa?
Ada soalan yang untuk yang K balance tu memang kita assume 0.167 lah.
Ya. Sebab we assume delta tu, redistribution is equal to 1. Kita tak ada buat apa-apa lagi so far. So when you analyze for the continuous beam, sometimes we need to reduce a moment at the support. So that's why we will use the delta. We need to calculate the delta after we do the redistribution. So sekarang ni tak perlulah. So you just assume K balance is equal 0.167. Okay. So before we go to the next topic, I would like to briefly remind you last week. So if you have a section, for example, any section, any section of beam or flexural member when at ultimate limit state, so we will have two things that we need to understand. The first is strain. The strain. And when we put the load, so the concrete will experience the strain. Strain is the deformation divided by the original length. Yeah? So we got the strain. The maximum for concrete is 0.035. Ultimate. This strain is before it's failed. So the maximum is 0.0035. So we need to remember this. Yeah, and then at the steel, steel here, so we need to put the value epsilon st. Yeah? So we cannot say that this steel is reach yield point. The yield point for the steel is 0.217, but we cannot say here the steel already failed. So we need to calculate actually. Yeah? So in design, we need to control the x over d to get the to obtain the steel also yield before the beam fail. Okay, after the strain, we also have stress. The stress and the strain. So the stress, the stress initially it is rectangular, parabolics, and then we need to modify to for simplification of the design formula derivation. So we change it from parabolic to the rectangular by the area under the block equal with the parabolic. So we need to reduce the s. Before that, before we assume it is rectangular, the s is equal to x. But when we assume it is rectangular, now s becomes 0.8x. So 0.8x is the stress block with the maximum stress by the concrete is 0.567 FCK. So this is maximum stress. Okay, and then the force, concrete force here is FCC is equal to stress times the area by the stress block, not x but 0.8x times b. And then here we must balance FCC with the FST. This is compressive load, and then this is tensile. So compress and tension must be equal. So with the Z, our lever arm is equal D minus half of this S. Okay, so that is the we have two rules. The force must be balanced or in equilibrium, and the moment also must be in equilibrium. So no matter where you take the moment, it must produce the same answer. Okay, from this concept, similar, we will apply to the flange beam. What is flange beam? Okay, this is a floor. So normally our beam will support the slab. This is the 3D and this is the beam, and this is the beam and column. So we can see that column will support the beam. So the beam will support the slab. Okay. Therefore, when the load acting on the slab, so the load will be distributed to the beam, meaning that the beam will deflect. The beam will deflect not only the section of the beam. So you can see here we have a beam, two category of beam. This is the beam. We already learned how to design this part. But now, because of this beam, also usually when we in the construction, we will cast this beam together with the slab. So during the ultimate state, when the load acting on the beam on the slab, the slab will deflect. This one will deflect, acting here. So it will deflect like that. Okay. So meaning that not only the slab deflect, part of the slab also, not only at the center section, but also in here, this part. So this part is actually part of the slab. So this part of the slab and the beam, we call it as the L beam. In this beam, we call it L beam, inverted L actually. And this is T beam. T beam when our beam support both slab here and here. We got a slab, so it make it a T beam. Yeah. So you can see that this is called flange. Flange is come from the slab. So floor system with the slab and beams are placed in monolithic pour. Monolithic means you pour together during the construction. Usually the construction floor and beam we pour together. So that during the design analysis at the design stage, we must consider part of the slab. Yeah, here is part of the beam as well. So it's called it as flange beam. So in this case, it's L, inverted L, and this is T beam. Someone want to join us. Khairil, Okay, slab acts as a top flange to the beam, T-beams and inverted L, as I mentioned just now. Okay, where's the eraser? Need to erase this. Okay, let's say this is the beam. Yeah? This is the beam. Part of this beam. Just now we look. Sorry. Just now we have a 3D diagram. Yeah? Let's say now we take this portion. Yeah. Take this portion. Right. Then here. Okay. This first. So this is the portion just now. Yeah. Now this is the column. This is the column. Yeah. So we must imagine before we design. We need to imagine how the crack will be. Yeah. So yeah, we assume that the beam will continue. Yeah. Maybe it's a continuous beam. So we assume that crack will happen at the span at the bottom here. So you can see a crack, tensile crack, and also at the top at the support. Yeah, the crack will happen at the flange. Yeah. Therefore, yeah, from this concept, yeah, so we can now place the reinforcement. You must remember that we must remember that steel is very good in compression and very low in tension. So that's why it's cracked here at the tension part. Yeah. Therefore, when you design, you must place the reinforcement, yeah, to prevent this crack. Yeah. So at the span, we need to put the reinforcement at the bottom here. You can see here at the bottom. So this is cross section at AA, yeah, cross AA. This is the beam and the flange, yeah. So the one that shaded area is the thickness of the slab. Yeah, therefore, since here it will experience the tension part, so we need to put tension reinforcement here, and this is compression or hanger. Yeah. Sometimes we don't need the when we design AS. That is not required. Therefore, we need to put a hanger. Someone who want to join? Wait a minute. Sorry. Is it Nazura or sign? Okay, so that's why we locate the steel at the bottom for this section. Yeah? Since the tension happen at the bottom. Yeah? Okay, for this, for the at the support, at the support we have a tension crack at the top. So now we put the tension steel at the top. Okay, but normally we put this tension at the rectangular beam area here. But if sometimes when too much steel, so we need to distribute here, over here. Okay. All right. So that is the location of the steel. Yeah? Similar with the previous in the rectangular beam. Yeah? Except we have a flange here. Okay. Now, before we proceed to the design equation, so we need to identify the dimension of the T-beam. Yeah? So in this derivation, the equation of the design, we focus on the T-beam, but actually it is also applies to the L-beam. Okay. Now we have a B. This is T-beam. This one, the beam. So we take this part. This is called B. Yeah? So actually this one is BEFF. Yeah? So this B can be B effective, or B flange. That the same B flange or B effective. So B. Yeah? Where is my cursor? Okay, B can be effective. Sometimes in the book it's called B effective. Sometimes B flange. Yeah, this B. And then the bottom here, the here we call web. And this is web. BW is B web. BW is actually is B for the web. Okay. So now we have two terminology. Yeah? The first is flange. This is flange, and this one called web. If in the rectangular beam, so we don't bother BW or BF or B effective and so on. But for the flange beam, we must remember we have two kind of B. The first is B effective or B flange. The second one is B web. Here is called B web. This is called web, and this is flange. Okay, D is from the compression part here, top to the bottom. And then H, the overall thickness is H. And this one is called HF, sorry, this one not T, HF. This is HF, according to the, normally we call it HF. Okay. What is H? HF is thickness of the flange, or sometimes floor, thickness of the floor. HF is flange or floor. Okay, so if you are given a floor plan, then the thickness of the slab is 100, therefore HF is 100. Okay, okay, that is the terminology for the flange beam. Yeah, this is for T, but if you have L, similar. Okay. Now, sometimes this type of section also called as flange. Why it is flange? Flange because the beam support the slab. So it is called flange. For example, maybe in a construction, we have a twin T, like this, twin T. So what we will do during the design, you need to imagine it's like T. Although actually in construction we have a BF, B-web 1 and B-web 2. But during the design, the B must be total, B1 plus B2. But when you put the reinforcement, you must concern with these two web. Do not change the twin T to the T, single T. It's only for us how to derive the equation. You can simplify it as this, meaning that when you consider the B at about B, B must be BW must be B1 plus B2, and this one as well. Okay, sometimes we have a box, culvert box. For example, maybe culvert. Sometimes culvert is circular, but sometimes a box like this. So if you have a cross-section box like this, so you need to analyze it. This is a flange, and this one plus this one. So we have a B here, BW, 2BW and B. So you have I section actually. You idealize, not the real section, but you idealize for the sake of design equation derivation. When you design, this will have one formula, and this one also. The formula derived from here will be different from this because of the BW here, BF. Okay. Okay. All right. Okay. Last time, last week, when we derive design equation, actually we need to consider the compression part, the compression part. The X over D is the main played the key role for the design equation. If for the rectangular, X over D is equal 0.45. So although you've got different shape, X over D 0.5 is still applies. Therefore, remember X over D must be limited to 0.45. Okay, so by doing that, in T-beam we have three type of design equation. And the first one we call it what we call it as neutral axis lies in the flange. What is neutral axis? Neutral axis is X. X, that the line that separated compression with the tension zone. The second one, neutral axis fall below the flange. Remember what is the flange? We will see it after this. Neutral axis fall below the flange with M greater than M balance. Still we have to use M balance. Okay, now the first principle, that is neutral axis lies in the flange. Okay. Okay, you need to imagine just now the floor. The load will acting on the floor. If the load is very little, maybe X will be only inside the flange. This is the flange. You see, this is HF, so this is the flange. For this, the first case, neutral axis lies in the flange. The X will be inside the flange. So this is happen when the load, as I said before, just now, when load is little. For example, for the classroom, there is no people, but there is no student in the classroom. So the classroom only support self weight of the concrete. So X will be inside the part here. That is the analogy. Yeah? So in this case, before that, look at this B. Remember just now, sometimes we call it B effective or B flange. This is the D. Yeah? D from the top of the compression. We assume that the load come from the top. So now the D is from the top of the here flange to the center of the steel. Yeah? So now let's say we will put two area of steel here to balance the compressive force here. We have a compressive force here. So now we need to balance it by putting two steel here AS. And this is the H. So what we'll do is that actually we need to draw the strain here. The strain diagram. Remember the strain diagram just now? Before we draw this, actually we have the strain diagram here. Here we don't, I don't show it to you because yeah, we assume that you already understand. Yeah? So this is the stress strain diagram. Yeah? So remember, we need to assume that here it will reach 0035. Okay, and this one is epsilon st here. So this is the stress block. Okay. Again, as I mentioned before, here our rule is that our philosophy in design is that the stress block will be rectangular. So it must be 0.8x. 0.8x. So you draw stress block here. Put it the force at the middle, FCC. So FCC is equal this 0.567 Fx times with the B times with the 0.8x, the area. This is the stress, so you need to multiply it by the area it acting. The area is B times 0.8x. So we have here FCC 0.454 FCKBX. The formula is similar, same with the rectangular section. Okay, now FCC must be balanced by the FST 0.87 Fy AS. So Z is D minus 4x. So the stress strain diagram is similar with the rectangular beam. Yeah? Why? Because the X is still inside the flange. Yeah? Okay. Now, yeah, what we imagine, yeah, this is the X is less than HF. Yeah? X less than HF. Okay, at one point, sorry, erase this. Okay, at one point, yeah, X will be equal with, sorry, at one point S, yeah, the stress block, this stress block, yeah, will be equal with this S stress block will be equal with the HF. Okay, yeah, this stress block will be equal with the HF. Yeah. So therefore, zero at X is equal to HF. So that is the possibility. Eh? Therefore, before we calculate the moment due to S equal to HF, now remember that moment, yeah, moment is equal, moment at the flange is equal FCC times Z, yeah, here times the lever arm. The previous stress block here. Yeah. So the moment, when you take moment about FSD, so we have FCC times Z. So we have we call it as MF, moment MF. Take moment here about FST. So you got MF. So we have MF, FCC times X. Okay, when the stress block depth equal to HF, so we have a new moment here. MF is equal 0.57 FCK BHF D minus HF over 2. Yeah, this is special moment. Special moment when S equal to HF. Yeah, so this is very important in design. So we call it as ultimate moment resistance when S is equal to HF. Yeah. So it has a meaning. Yeah? When our M from the analysis, we compare with MF. If it is less, then we design similar to the rectangular section. Let's see the example here. So we have an example here. Okay. A T-beam is required to resist a design moment M2 to 5 kN. If FCK 25 and FYK 500. So what is the area of steel here? Okay. So we assume that this beam is this cross section is at the midspan. Yeah? So therefore, the D is from the top of the compression here, top of the flange to the center of the to the web. Yeah, so we assume that this cross section is at the midspan. Yeah, so B is given here 1150, and the thickness of the floor is HF 100 millimeter. So the D is 320. Yeah. So how are we going to design it? Yeah? All right. So BW 250. Yeah? By using the moment that we obtained here. All right. Using this formula, this formula is very important. The important formula for the T section or L, even L, they use the same formula. So remember just now MF is equal 0.567 FCK BHF times DHF divided by 2. So you insert all the value here. So you got 440.1 kN/meter. Then this is the moment, yeah, when stress block, the height of stress block S equal with DHF. So if applied moment, yeah, less than MF, meaning that neutral axis lies in the flange. Yeah. So you design using the same formula with the rectangular section. Therefore, we calculate K. You look at the design formula for the rectangular section. Okay. Therefore, this formula of rectangular section. Rectangular section. Where is my cursor? Okay. Okay. Therefore, we have Km divided FCK BD square. Yeah? M divided by B FCK BD square. You put all insert all the value that you know just now. So you got 0076, which is less than K balance. What is K balance? K balance is 0.1. 0.167. Yeah. Therefore, it is the compression reinforcement is not required. Yeah. Therefore, you need to calculate Z. And Z, this one, just like the rectangular section, so you get 0.93D. Then proceed with the AS, the same formula for the rectangular section. So you got now 1738. Yeah. Okay. So how do we arrange? Yeah. So we must arrange in this area, the tension area. Yeah. This is the compression, and then compression happen at the top, so must be balanced by the tension steel we obtain here, the 4H25. Okay. Okay, any question? Ada soalan? Okay, now the next one is the if neutral axis lies below the flange. Yeah. Okay, since now we have just now we assume that X, in the flange, in the floor. Yeah. Now, what happens if X, if X goes beyond the floor? Yeah. This is happen when we have a bigger load. Yeah? So the X will be goes beyond to this section HF. Okay. All right. Similar with the rectangular section. Yeah. But you need to think. Yeah. The force here, remember the force FCC here, although the rectangular block is, although the stress block is rectangular, but we need to multiply the stress here with the area of 1, 2, 3, 1, 2, 3, meaning that we have the big F here. Yeah? Actually, we have a big F at the center. Yeah? Oh, like that. Yeah? Sorry, I will use different color. Blue. Okay. If you don't divide it into 3 different areas, for example, yeah, it's actually it is a, we don't know the centroid of this T. Maybe here. Okay, so we have a FCC like that. FCC. Okay. Yeah. So meaning that FCC is equal 0.567 FCK times the area of 1 to 3. Okay. Yeah. So 1 to 3 area, 1 to this area, the green and red, you can calculate the area, right? But the centroid, you need to find the average of centroid. So it's tedious. It's longer than it should be. So now what we can do is that we divide it into 2 areas, 1 and 2. Simplified. We make it simple by only consider 1 and 2. We divide it into 2 and then we add it together later. Yeah? So now what we do is that calculate first the number 1 area, yeah, with the rectangular stress block here. This one, 0.8x. Yeah? So the centroid, the force from the area 1 is FCC1 and is acting at the center of the area 1. Yeah, let's see here. Okay, FCC1. And then the part of 2, yeah, the second part is area of the green one. Yeah, so you can calculate also here. This one and this one plus added together, this one times with the 0.567. So you will get FCC2. Yeah, that is the idea. Yeah. So therefore, we have 2 forces here, 2 forces, and then later we will add it together. Yeah, therefore, in this section, T section, when X greater than HF, yeah, goes beyond HF, yeah, the concept is that both here FC1 plus FC2 must equal with the FST. Yeah. This one, FCC1 plus FC2, yeah, must be equal with the FST. Yeah. The force must be in equilibrium. Yeah. So compression force must equal with the tension force. Yeah. Also, the moment at anywhere, yeah, you take a moment, let's say you take moment about FST, yeah. So we have moment from the force FCC1 times Z1, FCC2 times Z2. So you add it together. Yeah, it must be similar if you take moment about FCC2. Yeah, so you must have the same moment. Okay. Therefore, now we have two rules, two philosophy. Yeah. The moment must be in equilibrium, and also the force, yeah, also must be in equilibrium. The last one here. Okay. So we have internal forces. FCC1 just now. So we have here 0.454 FCUBX. FCC2 0.567 FCK B minus BW HF and FST. So this is the internal forces. And lever arm, as you can see in the figure just now, Z1 and Z2. So Z1 is equal D minus half of 0.4x, 0.8x, and this one is HF divided by 2. Yeah, so Z2 is equal D minus HF divided by 2. Okay. Yeah. So moment resistance taking in from the steel. So we have FCC1 times Z1 plus FCC2 Z2. So this one, the equation is long. Yeah? So you got X. The important thing is that you got X here, because X will control the behavior of the concrete. Last week we have discussed, X will control the under the failure, the failure of the beam under reinforced and over reinforced. Okay, now ultimate moment of resistance. So from this equation, as I mentioned just now, X, we have X here. Therefore, we need to control X. So here we go, we have a imbalance. This moment become imbalance. When X we change, we limit to X balance. Here we go, we get 0.454 FCK BW and so on. Yeah. So we have the final one, 0.167 FCK BD square plus 0.56 FCK HF and so on. Yeah. Therefore, when we design, we need to calculate imbalance. Just now we calculate MF, then the next one is calculate imbalance. If moment from the analysis less than imbalance but greater than MF, we calculate previously. So the T-beam still does not require compression reinforcement. Okay. All right. In the formula, the design formula in the list of design formula and also in the book, we have this one, formula. This one BF. Okay. From here, imbalance, we can briefly obtain the ratio of BW over B and so on here. So imbalance can be calculated by using this formula, by modify this formula. Bring this BD to this left side. So we get this one. Okay. So therefore, this one we can summarize. This one is the BF. This part. Okay. So this part, we can replace it as BF, FCK, BD. Okay. Where BF, this one, the value. Okay. All right. So this formula can be obtained in the design list. Okay. Therefore, let's look the exercise. Okay. Oh, not yet exercise, sorry. We haven't yet derived the steel. Okay, to obtain tension reinforcement. Okay. Now we have just now we calculate M. We still calculate M balance. So our target is that what is the area of steel. So now therefore we use the formula. AS moment, taking moment about the FCC1 Z2. Okay, we take moment about this one. Here. Taking a moment about at FCC2, so you have FST times Z2 and then FCC times the the distance between FCC2 and FCC1. So you got this one. Okay. So you have this formula. By arrange the equation to have a AS here. So we have this equation. Again, we must control the X. X must be controlled from this formula to get the under-reinforced section. Therefore, we limit X equal to 0.45D as required in Eurocode. Then, we have the formula. The final formula is equal AS is equal M plus 0.1 FCK BW 0.36 minus HF divided 0.87 FIK D minus 0.5 H. So this one is applicable for H 0.36D. So this is the formula can be obtained in the book or in the list of design formula. Okay, now we look at the example 2. Now we use the same cross section, but this time we increase the applied moment from 200 to 5 just now to 275 to 445 kilonewton meter with the same concrete grade and also the steel. Determine AS. Okay. Now we don't know whether the beam requires compression or not, but let us check. Okay. First of all, we need to calculate MF. And MF from the first case. So we have MF. So just insert all the values. So just now we have already calculated. So we get 440.1. So our moment just now is 445. So it's greater than 440. When it's greater than the neutral axis falls below the flange. So since it's below the flange, so you need to calculate imbalance. So if it is less than, so we don't need to calculate imbalance. So imbalance, so you need to calculate imbalance. We can use the formula, this formula, or this formula, or this formula. You can use formula, this formula, and also this formula. It will give the same answer. Yeah. Now let's say we use the first formula. So you got 451.3. Yeah? When we compare with the moment, it's greater than the imbalance greater than the applied moment. Therefore, compression reinforcement not required. So how do we design? Yeah. So you need to calculate AS. AS by using the formula here we obtained just now. AS. Yeah. Just replace the moment, the BW, the D, the NHF. Yeah, very simple. So you got here 3815. So this is the steel that you can provide in this section. Okay, this is the arrangement. Okay. Okay. Okay, now we for the third case, yeah, we go to the third case. The third case, you can see that in the third case, yeah, when X greater than M balance, actually, yeah, this one. This is when M applied, yeah, M applied greater than M balance. Okay. Okay, so as you can see the diagram here, yeah, the diagram is similar with the second one just now, except we assume that we will need a compression reinforcement here. You can see compression here. This is compression reinforcement. This is similar with the previous one. So everything is similar except we have a FSC. FSC here. This one should be here. Okay, itu. Actually, I want to. Okay. Okay. Okay, sorry, my line is not stable. Okay, now actually this is a picture. Yeah, I put here picture, so I cannot amend that. So actually this one, if you okay, if you draw, make sure that this one must be in line. This one, okay. Meaning that FSC must be placed here. FSC, this FC must be placed here. Okay. So again, yeah, so we have three forces here to balance the FST. Yeah? Tension, this is tension force, and this is compression force. Yeah? So these three, yeah, you add it together, must be equal with the FST, and the moment also must be balanced. Yeah? So from that, with similar like rectangular section, yeah, we need to calculate the FCC is equal. FCC is this is from the concrete. FCK BWX, FST, FCC2. Yeah? I guess you already understand this one. Yeah? So the Z, so we have a Z1, Z2, Z3. And so the moment, look at the moment. Moment is equal FCC times Z3, FC1, Z1, FCC2, Z2. Yeah? So we have a long equation here. Yeah? It involves the tensions, the compression steel. It's similar with the rectangular section, except we have this one, B minus BW. In the rectangular section, we only have this part, yeah? But now we have this part. Okay. So after that, we will obtain the AS. Okay. When X again, yeah, during the derivation, formula derivation, we need to limit the X to 0.5D. So again, this formula, yeah. Formula X 0.5D, so you can get US. What is that? Sauda, please mute. Okay. Sauda or what? Okay. All right. After we have AS, this compression steel, yeah. Okay. We consider the equilibrium of forces. So FST is equal FCC1 plus FCC2 plus FSC. And then you can get the expression. This expression which contain X. When that is X, we need to consider by limiting X with 0.5D. So we will get the new expression here. Everything must be replaced. Every X value of X, every value of X must be replaced by 0.45D. Then you get the 0.8 FYK and so on here. Therefore, we already have AS. So now we have AS here from this equation. Now the example, example 3. Okay, the same beam, but now what happens if we increase the moment? The moment become 500 kilonewton meter. So let's say now there is a compression steel. Okay, so compression steel here, the central from the compression steel to the top of the compression zone here is D. We D dash, and we assume it is 50 millimeter. Okay. All right. Again, we need to calculate MF. So we already calculated just now. We got 440. Yeah, and of course it less than 500 the MF. Then we proceed to the imbalance to make sure that the compression is required. So imbalance we also already calculate just now. So we have our M greater than imbalance. So compression reinforcement is required. So the next step is by calculating the compression steel here. So we got 415 millimeter square. Then this is the AS using the formula given. So you have 415. So now we provide 5H25. So here in this example, I mixed two size of the steel. Yeah. So if you don't want, then you can use just one size. And the compression steel, so we have 4H12. So you can arrange like this. So the arrangement must be balanced. Okay. So this is the design procedure. Yeah. Okay, look at the design procedure. Yeah, here. The first is calculate MF. What is MF? MF is when these the stress block S equal to HF. So this is the formula. Okay. So if your M, applied moment, less than MF, therefore K is the design similar with the rectangular section. With B must be remembered. B is the B flange or B the big B. Yeah. So for the T beam, now we have BW and also the bottom here is BW. At the top, sometimes B, sometimes B flange, sometimes people be effective. So in this case, is the B flange. So calculate the Z, it must be less than 0.45T, and then calculate AS. So if M less than MF, so if M less than MF, greater than MF, therefore calculate BF. Yeah, remember BF just now? BF, this is using the formula. Or alternately, you can use the previous formula, but it is not in the design formula given to you. So might as well you use this one, yeah. So you get M balance here. So compare M and M balance. Okay, so this is the, if your M less than M balance, then use this formula to calculate the AS. Okay, so if M greater than M balance, so this is the formula. But remember here, B is the top here. BW is at the bottom here. Okay. So for the further example, you can see 2.6 to 2.7. Yeah. Okay. Okay, this is example 1. Okay, this is T-beam, yeah? Okay, example 1 using T-beam. Okay, so how about if it is L-beam? Okay, can you do example, this is extra example. The same size, yeah, but this time, let's say this T-beam become L-beam. Now our beam is only up to here. So it is L-beam with the B let's say 900. Sorry, my line is not stable. Okay, I will Just wait.
It's okay. Doktor.
Okay, I want this. Okay, copy. Okay. Let's say now we have example 4. Okay, now I want to change this. Not P beam, but it's L beam. Yeah? This is L beam. Sorry. This is L beam. L beam. L beam. L beam is required to resist moment. Determine the area of steel. Okay, so the B now I will change the B. HF. Okay, sorry. No, I will delete it. I think I better draw it. Okay, now if we have a L beam, sorry, L beam. Here is. Okay, L beam. Okay, so B, let's say we have a B here. B from here to here is B is equal 790 millimeter. Okay. Okay. HF is equal 100 millimeter, while D is equal 250 millimeter. Okay. So D, assume D is from here to here. Okay. At the moment is equal to 50 kilonewton meter. Then FCK is equal 25 Newton per millimeter square. Okay. D from here to here. Can you try? Can you try?
Yes, Doktor.
Okay. Okay, I will give you two exercise. Okay, now we have a. Sorry, I use different color. This different color. One. Okay, like this. Okay. The same, but I cannot copy it because I use Zoom, so I cannot copy it. Okay. Now the same dimension, but this time compression. No, the D is from here to here. Sorry. The D from here to here. Okay. So this is D. This is D. This one also. D, yeah. Okay. So can you find the design for these two? Yeah. Okay. So I think our lecture finished already for today, yeah, and I'll give you the exercise for the example 4. This is actually exercise for you to do tomorrow. We'll discuss tomorrow. So you have around how many minutes now? You can try it at home, so we can discuss it tomorrow. Tomorrow we will discuss how to find the B, right? And also some exercise. So for today, you need to do these two, yeah? Compare. Okay? Okay? Are you okay? Boleh tak?